That makes sense?
Okay, well that's the answer. That's the answer. So
Yeah.
it was completely psychological. The belief that oh great, at least I go faster downhill because I'm a bit fat.
Well, so
I
um,
can't I can't even get that from it. I've just got to accept it's hard going up. It's harder going up, and I don't get any benefit going down.
well, hold your horses there.
Oh oh okay.
There's more
All
to
right.
this.
Hello, welcome to Matter Over Mind. My name is Stephen, and with me, as always, we have plasma physics extraordinaire Thomas, my son-in-law, great
Oh,
chef. Not so good at taking photographs, but welcome, Thomas.
how you doing? Good intro. But yeah,
That's it
can't
then.
deny my picture taking skills aren't great.
Yeah, photographer, you're not.
Yeah,
Um,
no, I
but
understand how the cameras work, light wise and physics wise,
yeah,
but in practice, I don't know, it's tricky.
composition. Your problem is composition. Anyway, that's by the by. How are you? How's your day been?
Yeah, it's pretty good. Just cracking on with the analysis of the experimental data, which is exciting.
Mm-hmm.
Um, the design paper for also basically the simulation proof of concept paper for the experiment is very nearly finished. Well, it is pretty much finished, but we just need to send it to the collaborators so they can sort of
Right.
give the thumbs up on it, and then hopefully within the next month or so, maybe a little bit longer, send it to the publisher. So that should be exciting, and then we could perhaps do an episode on
Yeah.
that because last time I had to leave a few bits out
Yeah.
um, for what's the word to be secret. Don't
Ah,
want
okay.
yeah,
Confidentiality. Yeah.
yeah,
Cool. That's great. Yeah. Look forward to that. And obviously that'll be a paper, so I don't know whether people have access to that, but technically they can. So that will be really exciting.
yeah. It's a bit of a hefty one. It's a 30 pager,
Ooh. But
so
there's no formulas or anything like that on it. No maths, I should think.
no, there's a fair bit of maths. But
Damn.
yeah, you can look at the pretty pictures. It's fine.
Excellent. Now there are some nice pictures. I've seen some of the photographs or the pictures, however we want to describe them, of the experiment, and they look really cool. I say you should blow them up and make them into some sort of piece of art for your
Mm,
wall. I think they're really really cool.
yeah, for
Good.
sure. Yeah.
Okay. So today we're going to try and recreate a conversation we had in the car on the way home as a family from Scotland. So we went to Scotland as a family, me and Sarah, my wife, and you and my daughter Celine. And on the way back from Scotland, we sort of got talking, and I posed to you a question that I had a couple of years ago, really, when I was really into my cycling. And I asked you about this, and we had quite a long conversation about it. I actually can't really remember the conclusion, which is kind of good because I can be surprised again. And you sort of went a little bit back and forth on it because it's kind of a slightly tricky one. There's a lot. It's more complicated than it might sound. So I'm going to just put that to you, and for our listeners, I will kind of just summarise it on the Facebook group. So if people want to go onto that, they can see what I'm trying to say. But basically, um, I like cycling. I've not done much this year, but a couple of years ago, I was really into cycling. I've done a few quite long bike rides and everything. And I'm going to admit, my weight fluctuates quite a bit, and it also relates to cycling. When I'm starting to get heavy, I tend to look at my bike and think, okay, it's time. So I get the old bike out, and funnily enough, it normally happens this time of year, which isn't the time to get your bike out because now's the time to start thinking about wrapping up. But anyway, that's me. So obviously, I'm noticing different. I'm heavy or not so heavy, depending on my particular state at the time. And I got to thinking about what impact that has on cycling. And I remember saying to somebody, when you're overweight, going up hills is really, really hard because you're carrying, not only you're carrying the bike with you, you've got the weight of the bike, but it's mostly me. I'm the biggest weight. So you'll notice that cyclists are very, very thin. Professional cyclists, very, very skinny. So, okay, that's obvious. I think. I don't think there's very much controversy there. If you're going uphill, the heavier you are, the harder it is to push, because you're heavier, harder to get that hill. But then I used to think to myself, but coming downhill, if it's a really steep hill, you can reach quite fast speeds going downhill. Even an old duffer like me can get up to 40 miles an hour on a bike going downhill, and it's pretty exhilarating. But I thought it's got to be faster going downhill, because the heavier I am, the faster I'm going to go. So I thought that makes sense. I remember saying to somebody that. And then I got to thinking about that experiment that we've all seen, if you're into physics, which is where they set up a vacuum. There's a video of this. I'll put a link on the show notes, but you can see it in practice. So you've got a vacuum in this big area, and they drop a sort of heavy weight and a feather. Remembering it's a vacuum means there's no air resistance, and the two objects fall at the same rate.
Mm-hmm.
So we know this, and you'll tell me the physics behind this, but it's a principle that was discovered a long time ago. I remember learning about it in my Physics for You book, that orange one up there, and it means that it doesn't really matter how heavy something is, it will always fall at the same rate. Now, obviously, there's differences because of air resistance. That's why a feather will take longer than a cannonball, but if you take all the air out, there is no more resistance, which means they drop at the same rate. So I got to thinking, if that's the case, then when I'm bombing downhill, it shouldn't really matter how heavy I am or not. So that was the question to you. Does it matter? Does it make a difference if I'm heavier or not? And honestly, I don't know the answer to that. I kind of feel like I should know, but what do you think? Or what do you know? Not just think. What do you know?
Yeah, I've got my calculations.
You've even worked it out.
Yeah. So you're exactly right. With the experiment, when they drop the bowling ball and the feather in a vacuum, they both fall at the same rate, and that rate is acceleration due to gravity, because we're all on the same planet, which is about 9.81 meters per second squared. That's the acceleration a body will have when falling under gravity. This also works with two objects on relatively small scales. So obviously, in the experiment, they're in like a big tube, and they're dropping really far. If you just drop two things, above your desk, what's that, like 30 centimeters, they will probably also fall at the same rate, because it's not a long enough distance for air resistance to matter. So you can even test it if you have like a rubber and a piece of paper; they'll probably fall at the same rate, even on this small scale. So that everything falls at the same rate because gravity acts on everything seemingly equally. And why that is because of Newton's second law. So there's three, maybe four bonus laws of motion. There's the first one, which is a body will remain at rest or maintain constant velocity unless acted on by an external force. So basically, if you don't touch something, it's going to stay still. Or if you're in vacuum and something's traveling, unless you touch it, it will continue traveling at the same rate. So I mentioned this about space a while ago. If the spaceship runs out of fuel, it's just going to continue to drift at the same speed as it was when it ran out of fuel. So that's the first law. The second law is the force acting on the body is equal to the body's mass multiplied by its acceleration. So the force mediates an acceleration on a mass. That's the second law, F equals ma. And the third one is everyone's favorite, equal and opposite reaction. So if I put a little thing down on a table, its weight is pointing downwards, which means for the table to not basically cave in, it has to exert an equal force in the opposite direction.
Okay.
And the bonus one is conservation of energy, which it's not really a proper Newton's law, but it's relevant. So with those three things in mind, the second law is the one that matters here. So you've got the bowling ball or the feather or whatever in your vacuum, and we'll get to the cycling in a second, but we need to set up the groundwork. The bowling ball has a force acting on it, which is gravity. So it's weight essentially. It's pointing downwards, and so weight is defined by the body's mass multiplied by acceleration due to gravity. So essentially, the gravitational force is its mass times by that constant g, 9.81. So you know that's the force, and that's the only force in the system here. It's the force pulling the ball down. So that's the ball's mass multiplied by acceleration due to gravity. So that's force. Well, I've just defined force is equal to the mass of the body multiplied by its acceleration. Okay, so now we have mass times gravity equals mass times acceleration. Okay, well, mass is on both sides, so they cancel each other, right?
Yeah.
Mass isn't affecting one side more than the other. It's equally affecting both sides, so you can essentially negate them. There is no contribution more on one side than the other for mass, so you can kind of ignore it. So the result there is the acceleration of that ball is equal to gravity. So that's why mass doesn't matter. It doesn't matter. I could put 1 million kilos. It doesn't really matter because 1 million kilos are accelerating 1 million times gravity. Okay, cool. It's the same, the same difference. So that's why it doesn't really matter. Okay, but that's in a simple case where I'm dropping something vertically downwards. We're talking about cycling down a hill, so there's a slope element to it.
Yes.
Okay. So if you kind of break this down in a sort of simplistic view, imagine you're a block, just a cube, just to make life easier if you're thinking about the problem, and you're on an inclined plane, and I'm saying you're sliding down this plane, right? Why not rolling? Because rolling involves some extra bits which we'll get onto. But so for now, just imagine you're a cube on an inclined plane sliding down, right?
Okay.
So what are the forces acting here? So because you're on a plane, your weight is always acting downwards. It's always acting toward the center of Earth, so directly down. So there'll be a component of your weight traveling down the slope, essentially. So some fraction of your weight is down the slope. Also, because you're making contact with the slope, you'll have your normal force, so your sort of perpendicular force. That's the Newton's third law. Every action has an equal and opposite reaction. You're exerting a weight onto the slope, therefore the slope is exerting a weight onto you. So there's that force. And there's also friction. So you're not in a smooth environment. There is friction of the slope and the cube. So we'll ignore air resistance for now. There's two cases, and the answer actually differs when air resistance comes in, which maybe seems obvious, but we'll keep no air resistance. So there's no air. You're in a vacuum, sliding down the same. Okay. So
let me just interrupt for a minute. So just to clarify, so what we're doing is we're starting with a different experiment, which is we've got a slope, we've got two cubes, essentially, one heavier than the other. Is that right? And we're
for now, ignore two cubes, just one cube. You're the cube.
So we're trying to understand what the forces are involved in that.
Yeah, exactly. Yeah,
right.
yeah. So because by equating forces, we can determine basically what the driving terms are, and then how many if mass affects more of these forces than the other one, right? So we've got weight down the slope, we have friction, and we have the normal force perpendicular to the plane of the slope. So in terms of what's actually happening, we've got force down, so that's positive. We've got friction against your motion, so that's negative. So we've got the force is equal to weight, or portion of weight, minus friction. So that's your net force. And that's equal to your mass times your acceleration, always, right? So that's equal to ma, mass times acceleration. Okay, but also mentioned there's this resultant force here. Because at the moment, your weight down the slope is attributed to your mass. It's mass times acceleration due to gravity, and there's an angular component, so there's an extra term there, but mass is still there. So we know we have mass down the slope. So that's one term with mass minus friction equals mass times acceleration. So the question is, does the friction element also contain a mass? Because then that will answer whether you being heavier matters or not. So friction is defined by two terms. There's the coefficient of friction, so that's a materials thing. Each material will have a different coefficient of friction, essentially how grippy it is. And that is multiplied by the normal force. So remember I said you're exerting a weight on the slope, and the slope is exerting a weight on you. So that is directly proportional to the friction. How hard you're pushing against the surface matters over how much you grip on it, right?
Mm.
So the normal force is pointing out of the plane, and I mentioned before your weight is pointing straight down, which means there's a component of the force down the slope, but there's also a component of the force opposing that reaction.
Okay.
And because that's weight, we now know that the resultant force, basically the force of the slope on the cube, that has to have some relation to mass, because it's basically, to balance the forces, it's equal to some portion of your weight. It's the remaining portion of your weight that isn't down the slope. So your friction is equal to this coefficient, which is how grippy the surface is, multiplied by that resultant force, that reaction force, which is essentially a portion of your weight. So all your terms now, your driving force, your weight downwards, minus your friction, equals your mass times acceleration. All those terms now have equal scaling with mass. So there's mass times your friction, or your coefficient of friction, mass times acceleration due to gravity down the slope. And there's also mass on the other side by the definition of what force is, mass times acceleration. So mass equally scales on all three of those forces that are acting here, which means they essentially cancel. So to answer your question, in a world with no air resistance, it does not make any difference how heavy you are moving down a slope.
Right. Okay. Okay.
That makes sense?
Okay. Well, that's the answer. That's the answer. So,
Yeah.
it was completely psychological. The belief that, oh, great, at least I go faster downhill because I'm a bit fat.
Well, so
I can't even get that from it. I've just got to accept it's hard going up, it's harder going up, and I don't get any benefit going down.
so well, hold your horses there.
Okay,
There's more
all
to
right.
this.
Because we
So
don't. My bike isn't a block going down a slope.
no.
Okay.
So I suppose if you were to want to model it a little bit closer to your bike,
Yeah.
the friction element actually interacting with your bike is the wheel on the road. So that's that doesn't really matter. You're on a bearing essentially. So that friction doesn't stop your motion. But I guess you could argue, okay, well, the friction that is stopping your motion is the friction of your wheel spinning around its axle. So that would be the friction element, which
Okay. Is there nothing of the tire on the road though? Because obviously, the heavier you are, the more that perpendicular force is going to push down, isn't it?
that's true, but your wheel is freely rotating, right?
Yeah.
So if you model a perfect wheel, there is a single contact point. There is a bit on the curve, which is so there's an infinitesimally small bit touching the road, which is pushing it basically against your total motion, the center of mass motion, which is downwards.
Yeah.
But that is allowing your wheel to turn, which is allowing you to freely move.
Okay.
The friction is on the actual axle itself. That's the thing called friction. So I guess before we move on to the case with air resistance, maybe perhaps why you feel like you're moving faster is because you have more momentum. So you're carrying more energy. The heavier you are, the more energy you have as you're traveling down the hill. So suppose the hill stops now, or comes to a natural stop point, it becomes a flat. The heavier you are, you will travel farther if you're unpropelled.
Right. That's right. That was the conclusion that I came to on my bike one day. I thought, well, maybe it doesn't go faster, but you do keep rolling for longer. And that's what you're saying, yeah?
Yeah, exactly. Yeah.
So there is some benefit.
There is some benefit. So what happens now if you introduce air?
Okay.
So the setup is all as it was. We have force. The net force is equal to your mass times acceleration, as always. And that's equal to your weight component down the hill, your friction against that motion, and now there's an additional negative force or force against you, which is air resistance or drag. So you know that mass scales equally with friction, your weight component, and also just the definition of force, mass times acceleration. How does it scale with drag? So it turns out in the equation for drag or fluid friction, there is no mass component. It does not care about how heavy
Mm.
you are. It just cares about how dense the fluid is, how fast you're traveling, and your surface area. Right?
Mm.
Which kind of makes some
There you
intuitive
go.
sense, right? So if you
Yeah.
drop a piece of paper with its
Mm.
plain side facing downwards, it's going to, slowly kind of drift. If
Yeah.
you drop it, with its thin point pointing downwards, it's
Yeah.
just going to slide down, right?
Yeah.
And that kind of makes sense. The paper,
Yeah.
or like a parachute, right? The bigger
Yeah.
the
Yeah.
parachute, the more air it traps. Fine.
Yeah.
Okay, but how does this matter? So now we've got four terms. We've got mass times acceleration. Fine. We've got weight component, which is mass times acceleration to gravity, and then the angular component. We also have friction, which is the coefficient of friction multiplied by mass again, and then the remaining angular component. And we have drag, which has no mass component.
Mm.
So now your mass doesn't scale equally with every single term. So now it does matter. It does play a role. So there's a couple of ways of thinking about this. Purely mathematically, I can just divide through by mass. The mass disappears from all the terms apart from the drag term, the fluid friction, and that becomes it in the denominator. So it basically divides by it. So essentially what that's saying is the only term affected by mass is drag, and it's inversely proportional. So the heavier you are, the smaller the drag force. Right? The smaller the drag force, the less friction essentially is, or less fluid friction is acting on you. Therefore, the less it matters. So the heavier you are, the less you need to care about air resistance. So if you're infinitely heavy,
Yeah.
in a system where you're infinitely heavy, air resistance does absolutely nothing.
Wow, that's totally counterintuitive. There is another problem that I'm going to ask you. You probably thought about it already, but I'm going to come to that in a second. But I just want to pause on this.
Mm-hmm.
So it kind of, first of all, it surprises me that mass has anything to do with um, friction, actually.
Okay.
But obviously it does. Um, what I would guess is that friction would be affected. So if we think about air resistance,
Mm-hmm.
it's the hole you're punching in the air, the size of
Yeah.
the hole you're punching in the air as
Yeah.
you're going down the pike. And so I guess for me, the heavier I am, it also comes with the reality, the wider I am.
Yeah.
Yeah. So I would assume that my air resistance will be greater as I increase my weight. If I put on, I don't know, 20 pounds or something,
Mm-hmm.
then it's not just about the mass, it's also about the fact that it makes me physically bigger, which means that there's more wind resistance
Mm-hmm.
on my body. So I'm guessing that would also have that would have a negative effect. So although the mass element with um, my friction, you're saying mathematically has no effect. Um,
Providing the mass is large enough, in the limit of extremely large mass.
right.
I'll explain a way of thinking about
Okay.
that in a
Okay.
second. But so I mentioned before that the heavier you are, the smaller the drag force. Now,
Hmm.
that's one way of thinking about it. Another way of thinking about it is the larger your mass, the greater all the other terms are. The greater the mass times acceleration is, the greater your weight, the greater
Hmm.
the contact friction force, which
Hmm.
means they're so large, the larger your mass is, that they just completely dwarf the air resistance term. So that's
Okay.
another way of thinking about it. It's not that the air resistance is decreasing, it's that you're just not noticing it. It's so
Okay.
small by comparison to
Okay.
the weight that you're
Okay.
traveling through. But yeah, so as you said, generally as you gain mass, you gain surface area.
Girth, let's call it.
Girth, yeah, you gain extent. Um, so the term, so the air resistance, or I guess in this particular system, um, it scales linearly with both. So what that means is, so your drag force is equal to Coefficient of fluid friction. So similar to contact friction, there's always a coefficient associated with the material. So basically, how sticky the air is, if you will. So there's that coefficient. There's the density of the fluid. So traveling through water will affect you more than traveling through air. There's the velocity of the fluid, or if you that can also be your velocity if you assume the fluid's fixed. And then there's area. So area just scales. So the velocity is scaling squared. Your area is scaling just with just normal area. And mass in this particular system is also has the single power. So in terms of, they both linearly, I guess, with area, drag force linearly increases. With mass, it linearly decreases. So they basically perfectly cancel out. In principle, if you put on some mass, providing you gain the corresponding amount of area, then they kind of cancel out and it doesn't really matter too much. But what I would argue is mass has the neat property of just being tied to how much stuff is in you. It doesn't really care about your shape. Area is just a like a silhouette. So you'll presumably gain girth in 3 dimensions, right?
Yes. Yeah.
Area is a 2-dimensional thing, and it just cares about your silhouette. So if you're gaining a belly in front of you, well, that's not going to affect your silhouette, is it?
That's a very good point. Yeah, that's a very good point.
So I would argue, mass matters more in this sense because mass makes you grow in 3 dimensions. Area is a 2-dimensional thing, so your silhouette in at least one direction won't be changing as much.
Yeah, that's very good.
But yeah, so essentially, in a world with no air resistance, being heavier makes absolutely no difference. In a world like we live in that does have air resistance, your mass does matter, unless you're extremely heavy, and then it no longer matters again.
Okay. So when you say it matters, do you mean it? Do you mean I go just simple outcomes? When you say it in a world where there is air resistance, it matters. Does that then mean that I don't get the benefit of the weight? Is that what you're saying?
You do get the benefit of the weight. The lighter you are, the less you weigh, the more air resistance you feel.
Right. Okay.
So essentially, imagine the case with no air resistance. That's your maximum case. That's your perfect idealized system where everything's working your way. So that's like the pinnacle. That's as fast as you can go, essentially being accelerated by gravity down a hill. That's the pinnacle. Now in the real world, you have extra little bits that kind of hinder that perfection. In this case, it's air resistance. So air resistance essentially damps your acceleration due to gravity. So the heavier you are, the more you're approaching to this idealized state where air no longer matters. So the lighter you are, the more you feel air resistance, the farther you are away from this perfect case where there is no air.
Okay, that's good news then.
Yeah.
That's good news for us.
You can put on as much weight as you want.
If you can get to the top of the hill, you can go down fast. Yeah, okay. That's really interesting. So it does actually... So my first instinct was kind of correct. I mean, I don't know, you might be able to tell me the difference. It's probably not very much. But there is a small gain, let's say, going downhill, roughly the heavier you are. You tend to get gains top speed, would you say? So you go up a little bit faster. If you didn't pedal, this is assuming, we should have said that at the start, assuming you're freewheeling. So it's got nothing to do with your muscles or your ability to put energy into the bike. It's really just, get crouching down and just freewheeling down, so you get a bit of benefit from being a bit heavier, so you might go slightly faster.
Yes. I should note air resistance scales with the square of your velocity. So the faster you're going, the more air resistance you feel.
Yeah.
More so than mass. So basically you'd have to put on maybe not even twice the square of mass to counteract how much. So the faster you go, the more air resistance. So you'd have to
Yeah.
be really packing on the pounds. um,
Okay.
so it's
So yeah, yeah. Nobody's saying here that it's a good strategy, but we're just just interested in the theory of it, really. Yeah. Okay.
yeah,
And what
yeah,
about this? So we're saying that you're going down slightly faster if you're heavier. So when I say slightly, are we talking about a mile an hour, 1 or 2 miles an hour difference, or something like that, roughly?
um, it's hard to tell.
Okay.
Because it basically how long the hill is,
Yeah.
how
Yeah.
far you
Yeah.
how long you've been traveling for. It kind of all because
Mm,
we're talking about acceleration, not velocity. So acceleration is
okay.
the rate of increase of velocity. So how
Yes.
much? So
Oh, okay.
the acceleration due to gravity is again in free fall if you drop a ball, it's that that acceleration tells you how quickly the velocity is increasing. It's
Okay.
not telling you what velocity it's at.
It's not the top speed, or really, it's the speed of the acceleration. Or
Exactly. Yeah.
the
Yeah.
yeah. Okay.
The speed of the speed, if you will.
Yes.
um,
Okay. Yeah. I mean, a layman like me would talk about the speed of acceleration, but I know that doesn't really make much sense. Probably to you as a mathematician, but I know what I mean. Um,
yeah.
okay, but what about the this momentum that you've got? Is that added on top of that? So do I get that extra benefit that I can stay freewheeling for a bit longer
Mhm.
once the hill subsides and I'm on the flat now? I can carry on for a bit longer than a skinny person.
Yeah. Basically, yeah, because your momentum is your mass times your velocity. So um, you will have, assuming you're traveling at the same speed, a heavier person will just automatically have more momentum. Um, and momentum is essentially interchangeable with kinetic energy. It's not really, but it basically is. Well,
For
once you
our
get to
purposes.
well,
Okay.
well, there's a kind of a sweet spot. It's
Okay.
like the bell-shaped curve for complete laypersons. They're basically the same
Mm.
thing. Then you do
Okay.
undergraduate physics, and they're very different things. And then you get to my point in physics, where they're just the same thing again.
Okay. All right. Okay.
Yeah,
Okay. All right. So we're saying basically that extra weight does give you a little bit extra going downhill, and it takes you a little bit further.
yeah,
But in terms of your, so let's put the physics aside for a moment, and just from a cyclist perspective,
hmm
I would say that it's not worth it because the extra effort that it takes to get up the hill in the first place means you've wasted a lot of that your own personal energy. So cycling is really all about maintaining energy. Long
hmm
distance cycling is really so. You're all about trying to manage your energy through what you're taking in, what you're eating, and then the energy that you're expending as you're pedaling. So it wouldn't be worth it. And I can tell you from personal experience that it isn't worth it. The effort going up that hill is not worth the joy, even though when you're going down it feels fantastic. It saps you of the energy that you're going to need for the next one,
mm,
which was my experience on the Le Jog, which is why I didn't finish it.
yeah.
So yeah, that's just the sort of practicalities, but that's interesting. Okay, I know you've written down these these formulae and you've got your
hmm
workings out there. Is it okay if we copy that and put it
Yeah, that's fine. I mean,
on the
this
Facebook
is
page?
like basically when you first. Now, this is pre-university, but
Yeah.
post, um, you know, post regular GCSE, so which is like your
Okay. So A
15 to
levels
16
in the
degree.
UK.
Yeah,
Yeah.
so
Yeah.
this is when you learn your A levels. This is the kind of
Yeah.
stuff that you learn when you learn physics. It's
Mm.
yeah, it comes under what's called classical mechanics,
Mm.
which is your kind of your Newton's laws of motion, your pulleys, energy
Mm.
conservation, all that kind of stuff. So
Yeah.
this, to be honest, for me, this is what actually got me interested in physics. Not
Really.
the kind of cool, exciting space and
Ah,
quantum and all this kind of stuff. It's just this simple, everyday
yeah.
if I roll a ball down a hill, and one's hollow and one's solid, which one goes faster or which one hits the bottom quicker? Little things like
Yeah.
this, because it's
So
satisfying.
it's great. It's lovely to hear, and it's so great to hear somebody so enthusiastic about that sort of physics. Because I think you're right, and it's that that's made the world we live in, isn't it? I mean, I know we've come a long way with electronics and all of that, but really, if you think about the Industrial Revolution and all the great sort of things that have happened, and perhaps not so great things have happened, it's all down to understanding these basics. You posed another question to us actually as part of our discussion, which I'm proud to say I got right. Do you want to just do that one? What was the problem that you posed? Let's see whether our listeners get the right answer. Maybe we don't give the answer today. Maybe we leave that hanging. So
Okay.
pose the problem.
So was this the
The
circular one?
cylinder. Yeah,
Ah,
the
the
cylinder.
cylinder.
One
Okay.
cylinder that's solid and one that's um,
Hollow.
hollow in the middle. Yeah, yeah,
Yeah. So you have same setup. You have a
yeah,
hill, but
yeah.
instead of sliding this time, you're rolling. So there's a subtle
Mm,
difference between sliding and rolling. Um, and there's two cylinders dropped from the same height on this hill. However, one is hollow, one's just a cylindrical shell, and the other one is a solid cylinder. They both have the same mass. They weigh exactly the same, just the distribution of weight is obviously different. Which one gets to the bottom of the hill faster? So which one rolls quicker?
yeah.
The
And
the
and
the
we're
cylindrical shell or the
yeah,
solid cylinder?
and we're ignoring any sort of complications around wind resistance or anything like
Yeah,
that.
yeah, yeah.
We just imagine it's a vacuum again. So we're just interested in the cylindrical one that's solid and one that's hollow. Yeah. So we'll pose that. That's a question for you listeners. Which, if either one goes down quicker, what
Yeah,
happens?
they may be the same. Who
Yeah,
knows?
maybe same. Maybe one's faster than the other. What do you think? What do you think happens? So yeah, answers on a postcard, as they used to say.
Yeah, yeah. You don't have to show you're
Or
working.
yeah, you don't have to know you're working out. Just what is your instinctive beliefs about that, and pop it on the Facebook. Chat. Let's have a chat on the Facebook page on that one. The link to the Facebook page is on our notes, by the way, so anybody can access it. It's an open forum, so just pop on and say what you think the answer to that is, or you can put your answer in the YouTube comments if you want to, if you're on YouTube.
Hello, it's Editing Stephen here. So I'm going to interrupt this podcast episode to basically say I'm pausing it here. The conversation carries on for another half an hour and we get into gyroscopes, which is really interesting but quite complicated. So I think I'm going to leave this episode here and I'm going to create a second one that will stick on next week. So you get a bonus episode. So I'm going to say thank you very much for listening, everyone. I hope you enjoyed this episode of Matter Over Mind. And don't forget to sign up, subscribe if you're on YouTube. Find us on whatever podcast app you want to use and check us out next time. And we'll give you the answer in a couple of weeks about the question on the cylinders. So don't forget the bonus episode now, which will be all about gyroscopes. So check us out then as well. And for now, thank you very much for listening and goodbye.